a lot of good stuff here. And so let's go ahead and get started here. So hello, everyone, and welcome to the November NASA Night Sky Network member webinar. We're hosting tonight's webinar from the Astronomical Society of the Pacific in San Francisco, California. We're very excited to welcome our guest speaker, Dr. Frances Halzen from the University of Wisconsin at Madison. Welcome to everyone on the YouTube live stream. And we're very happy to have you with us. These webinars are monthly events for members of the Night Sky Network. For more information about the NASA Night Sky Network and the Astronomical Society of the Pacific, check the links in the chat. And before we introduce Dr. Halzen, here's Dave with just a couple of announcements.
Alrighty. Hi, everyone. I'll try to keep this brief, but I've got a few good messages for y'all. Let's see. First of all, just want to remind everyone to get ready for the PIN program. The PIN shipping department is going to be on the road for the next week and a half. So if you haven't ordered pins today, they will get to you. It just might be about a week and a half, early December before they get to you. That is me. And remember, also, if you want the pins for your outreach programs, to add reports to your events for this year to qualify. We don't just need the events on the calendar. We also want to find out how the events went. And so we just need information on just a few of those events. And you're really good to go. And our pin information page is on the Night Sky Network page and in your newsletter, and I put it in the chat. Also, once again, the NASA Eclipse Ambassadors Off the Path program is recruiting astronomers, and you'll be paired with undergrads to bring the science of eclipses and eclipse viewing tips to communities that aren't going to be on the path of totality in 2024. And don't worry, you can still travel to the path. We just want to help. We want you to help get your communities prepared for it. So if you're interested and would like to apply or know more information, go to eclipseambassadors.org, and also the link is in the chat. And
just kind of an aside about that, we have lots of undergrads who have applied, and right now we need amateur astronomers to apply. So, right now we've got an awful lot of eager undergraduates who we're not going to be able to partner unless you all apply.
Don't let those undergrads go lonely. Please support an undergrad and apply for the Eclipse Ambassadors program. Cue the Sarah McLachlan news. Okay. Another fun tip. The ASP's annual meeting is back, and it's virtual again this year, and it runs from December 8th through the 10th. The focus this year is space telescopes and bringing their science down to Earth. And astronomers, professional, amateur, unclassifiable, and informal educators are all invited to join this community, and really science communicators of all stripes. Go on down to the ASP annual meeting. You can find details at the ASP's website at astrosociety.org, and the link will also be in the chat. And one last final one. If anyone's paying attention to any NASA news today, Artemis 1 will be launching around, I believe, 1:04 a.m. Eastern time tomorrow, / late tonight. And you can watch all the coverage on NASA's YouTube channel, as well as on NASA TV. And it's going to be on probably about half an hour after we end tonight. So you have enough time to get some snacks for your Artemis launch watching. So enjoy. And that is it from me. Take it away, Brian.
All right. Thanks, Dave. For everyone on Zoom, you can find the chat window and the Q&A window down at the bottom edge of your Zoom window on your desktop. Please feel free to greet each other in the chat or to let us know if you're having any technical difficulties. You can also send us an email at nightskyinfo@astrosociety.org. Please put all of your questions in the Q&A window. That really helps us keep track of things. If you put them in the chat, chances are that we'll lose track of them. So put those in the Q&A window. And if we just hang on for just a moment here. All right, welcome again to the November webinar of the NASA Night Sky Network. This month we welcome Dr. Frances Halzen to our webinar. Frances Halzen is a I'm going to mispronounce this, Vias and Gregory Bright, Distinguished Professor of Physics at the University of Wisconsin-Madison. He's the principal investigator of IceCube, a cubic kilometer neutrino telescope buried in the Antarctic ice at the South Pole. IceCube's first observations of high-energy cosmic neutrinos garnered the 2013 Physics World Breakthrough of the Year Award. In September 2017, IceCube detected a high-energy neutrino from the direction of the blazar called TXS 0506 plus 056. This was the first ever evidence of a source of high-energy cosmic rays whose origins have been notoriously difficult to pinpoint since they were discovered over 100 years ago. Dr. Halzen is the co-author of Quarks and Leptons, a classic textbook on modern particle physics that continues to be used extensively throughout college campuses today. He's written a large number of publications and has written or edited several books. His essay, Antarctic Dreams, about the early days of Amanda, IceCube's precursor, was featured in the Best American Science Writing for 2000. Please welcome Dr. Francis Halzen.
Good evening. It's a pleasure to be here. Thank you for this nice, kind introduction. So I'll try to share my screen. And now I think we should be all set.
Yep, that looks great.
Okay, looks great here too. The topic of this talk is the Under the Ice Neutrino Observatory in Antarctica. And so I will try to explain in less than an hour a lot of things. So this is the menu for today. And as you can see, I have to introduce what a neutrino is. In case some people don't know, then I have to explain what neutrino astronomy is. Then I will explain that we actually built the first neutrino telescope, which is called IceCube. Then I'll show you the first neutrino maps of the sky, which were rather surprising to us and to everybody else, I think. And then I'll show you the first neutrino stars. So let's start, because this is a long menu. What's a neutrino? That's easy to explain. You learned in high school that the world is made of protons and neutrons that make nuclei, and then you put electrons around it, and then you get atoms. And that's what we're all made of and the universe made of. That's actually not quite true, because in Cambridge in the 1930s, they noticed that a neutron changed into a proton occasionally. And when that happened, the neutron changed into a proton and an electron. And you know from the simple rules of billiard ball physics, if the proton goes in one direction, the electron goes in the other direction. Occasionally, they saw in their experiment that this was not true. And so the electron and the proton would go in the same direction, which violates energy and momentum conservation. So Pauli, in his wisdom, said, well, we have to save the laws of physics, so there must be another particle, which was called the neutrino eventually, that takes off in the other direction and that restores Newtonian mechanics. And so the idea was they couldn't see this particle. It was just kind of an agent that made the possibility of changing neutrons into protons, which, by the way, is nuclear physics. And so that's where the name ghost particle comes from. It just was there to save physics from itself, and but you couldn't really detect it. So he told the fact that it would never be detected, which was really not true. In fact, Ellis and Mott reconstructed the distribution, the mass, which was close to zero of this particle. And basically, by today's standards, they detected the neutrino, but they never claimed detecting a particle. They couldn't imagine that the world had more than 3 particles. So, but you got the idea to build the universe, you need neutrinos. And in fact, of these 4 particles, the neutrino is the most common one in the universe. And without it, there is no nuclear physics. And without nuclear physics, we wouldn't have had a Big Bang, stars wouldn't explode, the sun wouldn't shine. You emit neutrinos, we produce neutrinos at Fermilab and at CERN. So neutrinos are everywhere where there's nuclear physics. And look at this picture on the top right. This is very important picture. You see, this is a nuclear reactor. It's covered with water to shield yourself from the charged particles that are emanating from the reactor. And you see that water is blue. So charged particles moving through water emit blue light, which is called Cherenkov radiation, but that's not important. The blue light allows you to see the particles. I'll come back to that later. And there is another important and unfortunate place where you produce neutrinos. That's about 20 kilometers above our heads in the atmosphere. Cosmic rays come into the atmosphere. They eventually meet a neutron or oxygen nucleus. They make a nuclear reaction, and the nuclear reaction make pions that decay neutrinos. The details of these are not important, but what is important is that we are bombarded all the time with neutrinos reaching us from the top of the atmosphere. And so imagine you want to look at neutrinos from space or from the universe like you do with light, then you look at these clouds of neutrinos and they never go away. So this is part of the story that I will have to explain to you. But so the conclusion is, if you detect neutrinos, you also detect cosmic rays, because you need cosmic rays, which are protons mostly, to make pions that decay in neutrinos. So if you find neutrinos in the universe, you will find where cosmic rays are accelerated. And so you are solving the cosmic ray problem, which is the oldest problem in astronomy. Cosmic rays were discovered by Victor Hess in 1912, more than 110 years ago. We have no idea where they come from or how they accelerated, but as you will hear at the end of this talk, that is changing. So, what's neutrino astronomy? This is the sky when you look at it with your eyes. I will always show the sky in galactic coordinates. So you see in the middle of the ellipse, you see the galactic plane. And so I am a particle physicist, I think, in terms of photons. And so these are photons for 1 electron volt. If you look at the sky in photons of a 10,000th of an electron volt, then the sky looks like this. That's the microwave background. And what you are looking at is 411 microwave photons per cubic centimeter everywhere in the universe. So if I move to the other side of the visible spectrum, this is the gamma ray sky. Now the energy of the photon is 1 giga electron volt and more. And so you see the sky looks again different. And so astronomers have looked at the sky, as you know very well, in all these colors of light, from radio to tiny wavelengths of high energy photons. But this game stops if I go farther into the blue to wavelengths of 10 to the minus 21 meter, the sky turns dark. There is no astronomy. We don't see the universe at these small wavelengths anymore. The energy of the photons is 1000 TeV. By the way, TeV, I live here 200 kilometers north of Fermilab. Fermilab is an accelerator that makes 1 TeV, accelerates 1 TeV protons. And at CERN, they make beams that accelerate 14 TeV protons. So I will use an accelerator unit as my unit in this talk. So this is another way of looking what I just told you. You see, look at the top. There are the radio waves, of course, that will play a role in this talk later. I go microwave, optical, X-ray, gamma rays, and then suddenly this game stops. The universe turns dark, and we have never seen the universe beyond this demarcation line. In fact, what this line shows is if you reach energies of about 1000 TeV, then you can barely see the galactic center. And the reason is shown in the next slide. Say you have a galaxy far away, just to take an example, that emits a photon of these energies. Well, it will never make it to your telescope on Earth because that photon will interact with one of these 411 microwave photons per cubic centimeter and makes an electron-positron pair. What's wrong with that? Well, now you have charged particles. With charged particles, you cannot do astronomy. And we know this very well because the cosmic rays themselves are charged, and their path is bent by the magnetic fields in the universe, by the magnetic field of inside our own galaxy. And so they don't tell us where they come from. That's why we have never solved the mystery of their origin. So neutrinos don't have that problem. They don't interact with anything. They are ghost particles, remember. They reach us from the beginning of time, from the edge of the universe. And so they can help us to look at the sky in the dark region of the universe. And so is this an interesting problem? And I'm a particle physicist, and so I'll give you my own answer. I remember when in 1991, a modest detector in Utah, the fly's eye detector, observed a cosmic ray of 300 million TeV. This is 100 million times the energy of the highest accelerator being produced at CERN in Geneva. We are looking here at particles with a wavelength of 10 to the minus 16 the times of the size of an atom. And so if you used state-of-the-art magnets that are used at CERN in Geneva, you would have to fill the orbit of Mercury to produce that particle. And, you know, how can you resist not to spend the rest of your life trying to solve this problem? So all we have to do is detect these neutrinos. And so that's the task we set out. How to build neutrino detectors, we know. You need water and you need light sensors. You see the photomultipliers on the wall of this tank. And so the water is rising and turning this into a neutrino detector. The problem with this beautiful detector in Japan is that the theorists in their wisdom told us that this experiment is 10,000 times too small to detect neutrinos from the cosmos. And even if you build one 10,000 times bigger, you are not guaranteed seeing anything. But that didn't faze us. And this is Moshe Markov on the left. And he had already told us at a talk he gave at a meeting in Rochester, New York in 1960, how to solve this problem. What you do is you put a light sensor deep in the ocean or in a lake, and you look for particles coming through the earth. If you see particles coming through your feet, it can only be neutrinos. Nothing else comes through the earth. If it's a muon neutrino, well, what do these particles do? They fly through your detector. You don't notice them. Neutrinos have no charge, electric charge. But occasionally, in our case, about 1 in a million times, they will crash in a nucleus in the ice, in the water, sorry, or the ice, and make charged particles. You get a nuclear reaction. They make charged particles. And if this is a muon neutrino, muon neutrinos produce a muon, and that muon will fly at the speed of light through your detector. It's charged, it makes blue light, because the speed of light in water is 3/4 of the speed of light that muon is going. It's going at almost the speed of light. It makes a shock wave. It's like a boat out racing the waves in the water. And the shock waves allows you to tell you where the muon and the neutrino came from. And so you have a telescope. So you get a flash of light that lasts about a millionth of a second. You reconstruct that flash of light and you detected a neutrino and you know where it came from. So I think I explained all this. So here is another picture. Here you see each of these dots is a photomultiplier. It has the size of a basketball. And when it detects light, it lights up. This is the online display of the IceCube experiment. And you see the neutrino came in, it crashed into a nucleus, it made this muon, and this muon travels at a speed of close to the speed of light through your detector. It deposits 2,600 TeV inside the detector. And that's interesting because with that much energy, it's very unlikely to be produced in the atmosphere. If you didn't get a picture yet, I show you the movie. So you see the muon comes through the Earth 11 degrees below the horizon and flies close to the speed of light to the detector, depositing 2,600 TeV of energy. So Markov actually suggested to implement this idea in the water, and there was a heroic experiment a long time ago in Hawaii that unfortunately failed. And so we had the idea that it actually may be simpler to freeze photomultipliers in ice than to put them in deep ocean waters. This may be counterintuitive, but history has proven us right. So where do you find ice to deploy such a detector at depth? At the South Pole. So you build a detector, or its component at least, in Madison, Wisconsin, in the Physics and Science Laboratory. The equipment goes to Christchurch, New Zealand. At the airport, it goes to McMurdo Base, and from there, another 3-hour flight, 9-hour flight to McMurdo, 3-hour flight to the South Pole. It can also go by ship from Port Hueneme, close to Los Angeles, directly to Christchurch or McMurdo. So this is the South Pole. That's what you see when you're at the South Pole. You stand here on 3 kilometers of ice, which is what we need for this experiment. And if you look in the other direction, you see a station, which is another thing we need. There is ice everywhere, but you need a lot of ice in a place where you have an infrastructure that allows you to build a particle physics experiment. And the other thing is, this is the station at night, so you can actually stay with the equipment 24 hours. So the South Pole was like a small miracle that happened to us that made this experiment possible. There was another thing that made this experiment possible. I cannot show you the glacier at the South Pole, but imagine this is a 3-kilometer ice sheet. We found that if you go 1.5 kilometers deep, slightly less actually, you find the clearest solid that nature ever built. You cannot even build a solid like that in the lab. The blue light I've been talking about can travel in that ice over distances of 100 to 300 meters. And so that's what you need to build a particle physics detector. Why is this ice so close? It was a serendipitous discovery, but it makes sense because you are looking at the center of the detector of ice that fell on Antarctica 50,000 years ago. It's ultra pure and compacted into the ice that's in the detector. So this is a picture of the South Pole. This is the South Pole station. The geographic South Pole is here. And this is the IceCube construction project, and everything comes in by C-130 planes. This adventure started very modestly. In fact, I was a theorist. I didn't have a lab, so I removed the ping pong table, the table tennis table we played table tennis on, and turned it into a lab where we put basketball-sized photomultipliers in pressure vessels and then hope to deploy them at the pole. These were 3 graduate students that were once theorists. This is a respectable physicist who now lives retired in Hawaii, Bob Morse, and this is Serap Tilaf, who is at the University of Delaware. So this is a picture of a 10-inch PMT. You buy it in Japan, that's easy. And then you melt it in the ice. That's not so easy. That's the second problem we had to solve. I'll come back to that. But here you see a picture of the South Pole in 2000. And by then we had deployed some 600 of these photomultipliers. And we observed events like this. And you see, this is a muon track going through the Earth, lighting up these photomultiplier tubes. And at that point, I must say in the whole adventure, this was the most exciting thing, the most exciting moment that we actually knew this was going to work. And I should point out that this was not always that easy. You're listening to a theorist, right? What do? You publish in Nature, claim you have solved the problem on how to discover the cosmic rays. You get help from the Economist, who was, they were intrigued by this experiment and provided our Amanda logo. And so then you say, now I'm going to finally build a kilometer cube detector. And so it becomes an industrial type project, more than 5,000 photomultipliers. If you could go in the detector that we built, it would look like this. You would see this clear ice. You would see strings with light sensors, 1 kilometer long, one every 17 meters. You go 125 meters away, you see another string. 86 of these strings fill 1 kilometer cube of ice, bubble-free ice below 1450 meters, ultra clear, with 5,160 of these light sensors. So to avoid all questions on this, how do you melt these things in the ice? You never drill holes. You change ice into water, sink the equipment in and let it refreeze. It takes a 4.8 megawatt heating plant, and it delivers 200 gallons per minute of boiling water through the nozzle of this equipment. So the first 90 meters are snow, and you just melt it. So you melt big enough hole for the equipment to go in. Then comes the hot water drill, which is basically a nozzle that puts out this hot water under pressure, and it falls by gravity, and 2 days later, it's at about 2.5 kilometers, and then you pull the drill out, and then you are ready to deploy your equipment. You realize ice is an insulator, so that water stays liquid for quite some time. So you have the time to deploy your equipment. So this is the hot water drill. It's like a circus train, but except on wheels, it's on sleds. This is the hose that goes to a depth of 2.5 kilometers in one shot. 2 days you are at depth. This is the power plant, 4.8 megawatts, 40 car wash heaters that are driven by generators that use normal fuel that comes in by C-130 plane at the time. So when this operation ends, you see the drill comes out, the hot water drill comes out, and you have now your column of ice transformed into water. So at this point, you move on 125 meters further, but here are 60 of your light sensors in pressure vessels with electronics that I will not go into, but you are ready to deploy them. So what you do is you attach them every 17 meters to a cable that brings down the power, but also brings up the information that your sensors detect. So all the light detected by the sensors is converted to a digital signal, which goes up to the surface on the same cable that brings the high voltage. So you can do this for about 2 months, and you see all these cables, 20 cables here from strings deployed in December and January of that year. And they go into this 2-story building that's filled with computers that reconstruct these light signals in the way I explained before. So here you can see IceCube in action. When you turn on IceCube, what do you see? You can guess. You see these neutrinos, and not just neutrinos, also muons, raining down on your detector from the atmosphere. But remember, that background is not there when you look up through your feed. And so here you see the detector reconstructing muon tracks. Sometimes these muons come in bundles. You see this bundle of cosmic ray muons flying through the detector. But we are interested in the tracks coming up and try to eliminate this mess. You should realize that you are looking here at 10 milliseconds of data. So what that means is we detect 100 billion cosmic ray muons per year, 100,000 atmospheric neutrinos, and we are looking for some small signal of high energy neutrinos reaching us from the cosmos. So in a background of 3,000 muons every second and 1 atmospheric neutrino every 5 minutes, we look at this cosmic neutrino. When around the time we had built this detector, actually the new scientist gave us a score of 6-1. They had a page you could bet. And you see you could bet on big science project. And they gave us 6-1 for discovering cosmic neutrinos. And I can tell you, I didn't sleep well after seeing that. In fact, they also gave 6-1 for CERN discovering the Higgs boson. And if you look here, this is LIGO. And they gave LIGO 500-1 for discovering gravitational waves. So you see the luck we had in the last decade. All these, despite their odds, all these discoveries became a reality. I never really worried once we built it what we would see, because you know, in your elementary astronomy text, right, you've seen these tables that tells you why people, starting with Galileo, build telescopes and what they eventually do with it. And the moral of this table is that you always do something interesting. In fact, more interesting than what you could imagine. And so, you know, when we built it and it worked, I was never worried we'll discover something. So we started taking data more than 10 years ago now. And so we were actually looking for these protons, but in a very original way. I told you how the universe turns dark because the photons are stopped by the microwave background. The highest energy cosmic rays, they are also stopped by the microwave background. They don't reach us. So they find a microwave photon, make a pion that makes a neutrino. And these neutrinos have enormous energies because only the highest energy cosmic rays can do this, like the particle in Utah. And it would fill your detector with light, and even a theorist can analyze the data. And we analyzed 2 years of data and we found nothing. Even though you can calculate this, and it's interesting why we didn't find nothing, but that's a different talk. But while looking at these 2 years of data, we found this event. In fact, we found 2 of them. And you see there is just serendipitously, and you see there's no muon track. That is because this is not a muon neutrino. This is an electron or a tau neutrino. In fact, we now believe this one is a tau neutrino. And so what happens is the neutrino interacts, it makes charged particles, no muon track, but these charged particles make blue light. And the blue light is like a bomb of blue light that explodes in your detector. And in fact, from the size of this bomb, you can tell what the energy is. And the energy is 1,000 TeV. And we know it very well because we see all of it in this case. And it's unlikely that the atmosphere produces a neutrino of this energy. And in fact, we found 2. We didn't claim anything. But then we went through the 2 years of data specifically looking for events like this. And they are not that difficult to find. This is an event superimposed on the data center in Madison, where I'm sitting right now. I sit here somewhere. This is the lake in the Madison campus. And the event you just saw, that's its size. It's at the size of like 5 city blocks. And there are 300 sensors that report detailed information on 300,000 photons that we detect. And so we looked through the 2 years for more events and we found 26 more. And so then we declared victory and published in Science that we had discovered cosmic neutrinos. And the next week we were declared the breakthrough of the year, which made us very, very nervous. But eventually, not only was this a discovery, we confirmed in a totally different way this discovery ourselves. You realize we were supposed, according to Markov, to look for neutrinos coming through the Earth, so coming from the northern hemisphere and look through our feet at the South Pole, and we did that as well. And we discovered cosmic neutrinos a second time. In fact, we have by now discovered them in 4 different ways. I won't go into. But here you see the number, this is a plot that just shows the number of muons we detect as a function of the energy of the neutrino. And you see this is 100 GeV, a tenth of a TeV, my unit of 1 Fermilab accelerator, and that's the threshold. Lower energy neutrinos in this analysis we don't see. We can see them in other ways, but so you see your detector becomes more efficient, you see more and more neutrinos, but these are neutrinos coming at the rate of 1 every 5 minutes from the atmosphere. They're pretty useless. Then you see when you go up to higher energy, the atmosphere is not very good at producing higher energy neutrinos. We understand the mechanism. We can predict this flux, actually. And you see, we predict and measure it. It's the blue line. But then if you reach about 100 TeV, you see, we see more neutrinos than are produced in the atmosphere. And of course, they come from the cosmos. They come at a rate of more than 200 per year, and they are in this tail. So with the Markov method, we confirmed our previous measurement. So what do we learn from these measurements? First of all, let me show you, this is a map. I cannot show you all our data. This is 1 year of data. That's the resolution of PowerPoint. There are 138,000 neutrinos in here, and 200, slightly more like 220, come from the cosmos. The purity of this sample is 97%. So we beat this background with having a pure sample of neutrinos with only 3% background left, in which live these 200 cosmic neutrinos. 12 of them are nicely separated, about 1 a month, come nicely separated from the atmospheric background. And so this happens for energies that are about 100 TeV or more. So let's just look at the highest energy neutrinos. And what do you see? We don't see the galactic plane. Now, as you know very well, we live in a galaxy, and we are first supposed to see by simple geometry the sources in our own galaxy. We don't. We see the rest of the universe. And that's consistent with this picture, or you know, that neutrinos come from the beginning of time and the edge of space. And well, there they are. And they actually outshine our own galaxy. I won't come back to this, but you know, the galaxy is there at a level of 10%, and I'm not allowed to tell you, but you know, you will find out about it sometime when science allows me to tell you. But I mean by Science magazine. So no galactic plane. The other surprise is this is the total light in the universe at different wavelengths. And you see here, this is the microwave background. So this is what astronomers call nu F nu. That's the energy that's reaching us from the universe in terms of microwave photons. It dominates the sky. This is the radio background. Here you see, you go through the different wavelengths of light, the infrared, ultraviolet, the X-rays, and then you see the gamma rays, and then you see the universe turn dark. So this is actually the remnant of this gamma ray flux. This gamma ray flux lives in the universe, but it gets shifted. It doesn't make it with its full energy through the microwave background. And so we observe it cut off. And this is an early measurement of the neutrino flux. And this was a huge surprise. Our neutrino flux we see is larger than the flux of light in the universe. This was not expected at all. Cosmic rays and neutrinos were supposed to be some boutique science done by original people and not paid much attention to. Well, they dominate the dark universe, and we'll have to deal with them if we ever want to understand the highest radiation that reaches us from there. This is, of course, a great opportunity to do astronomy. So I told you all these things, and so the real question now is, where do they come from? You realize we have discovered, we measure about 1 a month, that we can point back to their source. We've been doing this for 10 years. So they have a resolution, an angular resolution of better than 0.5 degrees, not great. But guess what? We didn't find the sources. So what did we decide to do? Well, we decided to throw our data overboard, which is called multi-messenger neutrino astronomy. So here, top left, you see this picture. So this is a flash of light made in a microsecond. And all this information you see and don't see in the picture, goes up to our computers. About 30 seconds later, the computers tell you what the direction of this neutrino is, and then you send it over iridium satellite to every astronomer in the world by astronomical telegram who wants to pay attention. Soon after we started this, we struck gold. This is the telegram sent to the astronomical community. This is the neutrino. It has an energy of 290 TeV. Remember, the demarcation line where the neutrinos become interesting is about 100 TeV. It comes from Orion, and we send the coordinates to the astronomical community and found out that this neutrino points to what the astronomers call the blazar, TXS 0506 plus 056, one of 1,000 blazars, nothing special about it, except at the time it was flaring. You know, blazars change their flux over all time scales, and this one was flaring. So that made the plot thicken, but this observation can still be accidental. It has a probability of being accidental of 1 in 1,000 times. However, later it was discovered by ground-based telescopes, MAGIC in the Canary Islands, that it emitted 100 GeV gamma rays, and as it's 4 billion light years away, that means it really produced TeV gamma rays that trickled through the microwave background down to the telescope at 100 GeV. In fact, we had no idea whether any astronomer ever paid attention to these telegrams, but it turns out that more than 20 telescopes were looking at this in the direction of this neutrino at some point after it was detected. In fact, an optical telescope was looking at this neutrino 73 seconds after we sent out the information. Then it was seen by Swift, by Fermi, and here a set of telescopes were looking at it to try to identify the host galaxy and to measure the distance to the galaxy, which eventually happened months later when the high energy radiation stopped blinding the optical telescopes. So we published this multi-messenger observation, but if you notice, there is a second paper following the multi-messenger paper by IceCube. And what we did is we went to look at the 9.5 years of data we had collected before this event. Now we had a place to look. And what we saw was basically nothing except for this huge burst in 2014. Look, this is a burst I've been talking about. It's a burst that's dominated by this one neutrino. But in 2014, we saw this burst that dominates the emission of this galaxy over the last decade. The energy of these neutrinos is Eddington. It's at the Eddington luminosity for this galaxy. We have enough events to reconstruct a spectrum, which is e to the minus 2.2. And it was not accompanied by gamma rays in this case. In fact, I have my doubts about this, but I won't go into this. It turns out this was the observation, by the way. There is the galaxy. This is where these neutrinos reconstruct. The galaxy, of course, has a supermassive black hole, and it has a jet. But we learned later the hard way, by not being able to model the jet, that most likely the neutrinos are produced close to the supermassive black hole. Now, before finishing, an update. I have already introduced this map and already told you how difficult it is to find sources of this map. However, if you look at the 10 years of data, this map is not totally uniform anymore. And it has there is evidence more than 3 sigma actually, that this map is not isotropic, and it's actually due to 4 sources that stick out. By the way, what you're looking at is not a map of the neutrinos, it's a map of the p-value, the probability that in a place like this, for instance, there is a cluster of neutrinos, a neutrino star, with on average higher energy of the neutrinos. So it's just the probability that there is a neutrino source anywhere in the sky. And actually the highest probability is here, and that's NGC 1068, a nearby active galaxy. And we observe it at 2.9 sigma. After you take into account the look elsewhere effect, which we can actually calculate, it's totally given. There are no hidden trials. This is a real probability. So the question is, are these interesting fluctuation? Is this a fluctuation, or is it is it a real source, or just fluctuate at an interesting place? So we decided to answer this question by, after 10 years, making a major overhaul, improving the detector. So we improved the detector geometry, we improved its calibrations, and we now calibrated each of the 5,000 plus light sensors individually and reconstructed the data with the individual calibrations. And as we had kept all our raw data, we can, of course, everything we do, we can apply to the 10 years of data we have. So we learned more about the optic of the ice. We have a program going on that keeps studying the optics and improving our understanding. And the optics, of course, is the medium, the ice, the optics of the ice is the medium through which the photons we detect propagate a Cherenkov light. And so the better we understand the ice, the better we can reconstruct the Cherenkov cones and light flashes that I've shown you before. So we improved the angular resolution. It's now 0.3 degrees with no systematics to be included. It's absolute 0.3 degrees. I know it's not great, but it's quite an achievement given what we expected. And then, because we modeled the point spread function of the telescope with Gaussian approximation, we were partially blind because we knew this was not a good approximation. For instance, if you have a neutrino pointing there in that direction, the blue line was our point spread function around the direction of this neutrino, where in actual data tells you it's this, the simulation tells you. So if you model this correctly and you have your point spread function correct, you improve the vision of your instrument. You're no longer partially blind. And so we implemented all these things in one shot and applied it to 10 years of data. And this is what happened to NGC 1068. This was the observation before recalibration and reanalysis. By the way, I forgot to mention, we made improvements in the energy and pointing resolution also by using modern machine learning techniques rather than making cuts on the data. So by improving the calibration, you see how the neutrino moved closer to the actual position of the source, and how eventually the resolution became better. And so we moved from 2.9 to 4.2 sigma. And you see, whereas in the early analysis, we found occasionally better and worse evidence for the source, in the new analysis, every year we see exactly the same thing. And so that builds up after 2 years to this result, where we now point better. We have 80 neutrinos, 79, coming from this direction with higher energies on average. So this is a solid, and as I said, this 4.2 sigma includes all the trials to do these measurements, which we count in a blind analysis. So this is a real probability. So another way of looking at this result is to do something very simple. This is the distribution of the neutrino directions around the source. So this is the direction of NGC 1068. This is the background in orange of atmospheric neutrinos, and you see this excess of some 80 neutrinos in the direction of the source. What you don't see in this plot is that this excess, also on average, these neutrinos have higher energy, and the combination builds up to this 4.2 sigma. So there is another way of looking at this result, and that is to look at the flux of neutrinos you observe as a function of the angle, the zenith angle. So the 0 is the horizon, and 1 is neutrinos straight through the Earth from the North Pole to the South Pole. And so there you see NGC 1068, and that's the sensitivity of our telescope. And the sources we look at are mostly around the sensitivity of our telescope. This is the 5 sigma discovery, and you see these sources sticking out. And it's because of these sources that I told you that the map is no longer isotropic. Look what the second source is. It's TXS 506. Although we are not looking for spectacular neutrinos or flaring events, even if you just look for the time-independent emission from the sky, you find this source again. And so I don't think there's much doubt anymore that we have established TXS 506 as well with this analysis. You can do, I won't go through the rest of this plot. It makes different assumptions on the spectrum, and then these sources can rise and fall. But the conclusion is that we, besides TXS 506 at NGC 1068, we also see NGC 4151 emerge from this table. And I like this because you notice the NGC 1068 and 4151 were the 2 sources that were identified by Seifert in 1943 with as what we now call Seifert galaxies, with active cores that are opaque to gamma rays and that have these broad lines. So this is NASA's illustration of an active core at the center, the obscure core at the center of the active galaxy. And the physics makes sense. You know, somewhere between the accretion disk and the base of a weak jet and the black hole, particles are accelerated, but they are accelerated in this region that is obscure, has a high density of protons, more than 10 to the 24 per centimeter square, and from which gamma rays cannot escape. And so that's probably the accelerator of the 80 neutrinos I just talked about. Now, I'm going to conclude at this point, and the question is, have we solved the cosmic ray problem? Of course, protons that are cosmic rays make inactive coarse neutrinos. So, well, I let you judge, but it's too close to call victory. What I want to emphasize, actually, and what I hope I have tried to convince you of, is that with multi-messenger astronomy, we have the tools to finally solve this problem. So let me conclude at this point, and thank you. And I want to recognize that I didn't do this all by myself. And so IceCube is a collaboration of about 350 physicists, even some astronomers. And so I want to leave you with this picture. It are all these great young people that did the work that I've been talking about. Thank you very much.
All right. Well, thank you very much. That was really, really interesting. And it's remarkable how we could use these this detector in the ice in Antarctica to determine some of the phenomena that's out there in the universe. So we have a few, quite a few questions here, and I'm going to apologize right away to everyone that whose questions we don't get to. So we've got time for a few though. So we had a couple of questions having to do with the detectors, and they're wondering whether or not they suffer displacement or damage because of movement within the ice sheet, and whether you have to replace them every once in a while.
Well, the last question is easy. You cannot replace them. They're frozen in the ice forever. The other answer to the question is they move. They are sitting in a glacier that runs off the West Antarctic mountain range. And so the detector moves 10 to 11 meters every year with the glacier. But at the bottom, the temperature is close to 0 C, and so it floats on ice. We don't detect any relative movement of the detectors relative to each other. So it's totally stable. Also, we have lost, a handful of the 5,000 under 60 in the last 10 years. You lose quite a few when they refreeze into the ice, because this is a violent process. I won't explain why, but you lose at a level of 1%. But after that, the detector is frozen in the ice. The electronics is at -50 C, and nothing happens to it. You have a totally stable detector. Some of the photomultipliers have been in there for more than 15 years now.
So here's an interesting question. And so do you feel that there are considerably more cosmic neutrinos than the current sensitivity and density of your detectors is capable of detecting?
No, we detect the diffuse flux we detect gives us a measure of the total energy or the total flux of neutrinos that reaches us from the cosmos. And we now know 90% is extragalactic, and the galactic plane is at the 10% level. So we know how many neutrinos reach us. We understand the sensitivity of our detector. Remember, I didn't point this out, but by measuring the cosmic ray flux, you calibrate the cosmic ray, the atmospheric neutrino flux. You calibrate your detector. And so we know very precisely what the sensitivity is. We have seen individual event where we can calibrate our detector at high energy. So we understand its sensitivity. We see how many neutrinos we detect, so we can reconstruct the flux of the universe. So if we want to detect more than one good neutrino a month, or more than the 200 plus per year in that map, we have to build a bigger detector.
So a couple of people asked if using solid state detectors, photodetectors, would be eventually better than they.
No, of course, you know, everybody is moving to silicon PMTs, and so in these experiments, you need superb energy resolution and superb timing resolution, and photomultipliers are still it.
Okay.
Also, they are cheap.
Yeah. So that's, this is an interesting one. And so I'm just going to read it the way it is. The muons are charged, so they're generating their own Cherenkov radiation. But the neutrinos are only detected by scattered electrons. So how can you deduce a direction from the scattered particles when there are so few events?
No. So the neutrino, let's take the case of the muon neutrino, because that's the one the question is referring to. As you saw in the picture, the neutrino interacts. The muon moves in the direction of the neutrino. And then the Cherenkov flight tells us the direction of the muon. So if you know the direction of the muon, you know the direction of the neutrino. Now you may ask, how do I know that? Well, as you told in the introduction, I wrote a textbook about it. That's why I know it. But there is something called the standard model of particle physics. And all the physics by which the detector operates, like how much light the muon emits, how much light our photomultipliers detect, how the alignment of the muon and the neutrino at high energy, all that is given by the standard model of particle physics. So we know the physics by which the detector works, even though I have not gone into it in detail.
So I want to come back, another question here, and I think it's related to one that you just answered a moment ago. So this person wondered that if the universe is filled with neutrinos, how come the telescope is only detecting 200 per year of the ones that you're interested in?
Well, first of all, remember, 200 is not a small number, because for every one of those, there are 1 million that we don't detect and fly to the detector unnoticed. So then the other question is, what's a large flux and what's not a large flux? It's large in the sense, well, once we understand the sources, I will be able to answer let me assume cores of active galaxies are the accelerators of the cosmic rays that make the neutrinos. Then I can answer the question, because I know how many active galaxies there are. I can integrate them. I know how many they each emit. I can integrate them over the history of the universe, and then I can tell you the total flux in neutrinos in the universe. We are not quite there yet, but anyone can do that calculation, actually. I'm sure every theorist working on this topic has already done it. But that's a flux. Is the flux large or not? Well, it's large because it's higher than the flux that reaches us from the universe in light, as I showed on one of these slides.
Okay, I'm going to do 2 more questions here. And again, I apologize to those of you whose questions we're not getting to. And so we have a question here is, do we know why neutrinos exist? Are they needed for the universe to exist? And I think that one of your slides—
I think one of my slides made this clear, right? We wouldn't be here without neutrinos. There would be no sunlight, no Big Bang, no supernova remnants from which the material, some of the material in our body is made. So neutrinos, no nuclear physics, no universe.
So basically they're essential for the—
They're totally essential. So that's why I said that the world is made of neutrons, protons, electrons, and neutrinos. There's no universe without neutrinos. And by the way, if you count them, they're dominated by the ones made in the Big Bang. There are more neutrinos in the universe than electrons, protons, and neutrons. So that's another way to answer the question. So these are not our neutrinos, which are relatively rare and have high energy. But the ones made in the universe, that's the largest number of particles in the universe, are these neutrinos made in the Big Bang, which have an energy of about 2 Kelvin instead of 3.
And I lied. I'm going to ask 2 questions of follow-up to that one, because if there's that many neutrinos, does it have any implications for the identification of dark matter, or the nature of dark energy? Does it have any relationship to that?
It may not. As we don't know what dark matter is and what dark energy is, anything is possible. Although we try to do some things that to address the question. First of all, we look for dark matter in ways that I cannot explain in a short time, but we look actually for neutrinos, high energy neutrinos, not nuclear neutrinos, coming out of the center of the sun. And that's a very sensitive measurement of the concentration of dark matter in the sun. But as I said, that's a different question. But we also look, for instance, when the neutrinos reaches from the universe, we look in the direction of the galactic center. And if there is a lot of dark matter there, which we are rather sure there is, right? There is a concentration of dark matter at the galactic center. So we are actually looking whether neutrinos that arrive from the direction of the galactic center are blocked by dark matter. And we don't see any evidence. And so we can put a limit on the cross-section for dark matter to interact, neutrinos to interact with dark matter.
Interesting.
Tiny cross-section. So we do all kinds of things related to dark matter. But again, this is a very long talk, which is different. What I talked about 1/3 of the people in IceCube are working on this. All the others are doing something else. There are probably 21-hour talks that I'm not about to give now.
Okay, last question for sure. And I think this, what if there is a nuclear detonation around the Earth someplace? Would the array detect that?
Yes. It's not quite big enough. We did these calculations many years ago. I think you would need about 10 IceCubes or more. Less than 100, more than 10. Now we are thinking about next generation detector that's 10 times the volume, but you would, and then you could detect a nuclear explosion anywhere on Earth. So it's something, I think that's a bit unrealistic, but not impossible. The neutrinos, unlike the light you detect from a nuclear explosion, the neutrinos would instantly tell you what the power of the bomb is. It's the only way. So it's an interesting measurement, but yeah, if someone wants to build 100 IceCubes, we'll be ready to take the data.
There you go. All right. Well, thank you so much. This is really interesting. And thank you for joining us. And thank you, everyone, for tuning in. So you'll be able to find this webinar along with many others on the Night Sky Network website in the Outreach Resources section. Each webinar's page also features additional resources and activities. Tonight's presentation will also be on the Night Sky Network YouTube channel. And join us for our next webinar on Tuesday, December 13th, when Dr. Robert Nemiroff returns to share with us the best of the astronomy picture of the day for 2022. So keep looking up, and we'll see all of you next month. And thank